Okay, so I forgot to record yesterday, which means I do want to do a recap so that we get, the short version of the notes and one example, and then we'll get back to 4.4 notes. Okay, so yesterday we talked about finding concave up or concavity and inflection points. Okay, so again, I did this yesterday, but forgot to record, and we're doing the steps, but just simplified. So step 1, find second order critical numbers. Next, use step 1 to create test intervals on a number line. Okay. Then test points in each interval to make a sign chart for f double prime of x. Okay. Based on those signs, find inflection points. I'm going to do one more example. It's a pretty clear, easy to see graph, but we're going to go through steps for increasing, decreasing, max, min, and then concave up, concave down, and also inflection points. So, it's f of x equal to x cubed plus 1. First, we're going to find increasing, decreasing, max, and min. Okay, so this is going back to previous notes where we do first order critical numbers. Let's get started. So we're going to find f prime of x and then see if that's ever undefined and what happens if that is equal to 0. I'm going to take 3x squared plus 0. And think about, can this function be undefined? Nope. I don't have to worry about any roots, which could lead to imaginary numbers. I don't have to worry about dividing by 0 because there's no division, we're just going to put in x and square it, which it will be like a real number squared is a real number times this real number is still a real number. Then we also look at f prime of x being equal to 0. This in here, get x equal to 0. So we found those critical numbers, and we create a sign chart for f prime. Okay. When you look at f prime, we're considering increasing and decreasing, so intervals that the function increases on or decreases. We plot this critical number, 0, and the interval is negative infinity to 0, and another one from 0 to infinity. So test some negative number, like negative 1. Negative 1 in f prime of x would be 3 times negative 1 squared, which is positive 3, which means you're increasing. If you put in positive 1, 1 squared is 1 times 3 is positive 3. So the function increases for all real numbers x, and there's no max, there's no min. Okay, so x is increasing for all x that exist in the real numbers. No max. Or min. So we do f double prime of x to look at concave up, concave down. Next part. We do intervals for concave up and concave down using a sign chart for f double prime. So we start out with Scratchbook and get those second order critical numbers. Okay. Second order, like take the derivative of f twice. F double prime of x would be the derivative of 3x squared. We get 6x. Two things to look at. Is this function ever undefined? Do you have any roots to look at, or do you divide by the variable? No. Every real number in here will be some real number times 6 is still a real number. Not undefined. What if it's equal to 0? Okay, put 6x right here, equal to 0. X would be 0, and then we start a sign chart. Okay, we want to check out f double prime. That looks like, well, instead of concave, we're just going to put up or down. So concave up or concave down is what we're looking at. Okay, plot this critical number for f double prime. And your test intervals are the same as before, negative infinity to 0, 0 to infinity. Put your test point into f double prime. So you're putting -1, multiply it with 6, and get -6. So it's concave down. If you pick +1, 1 times 6 is 6, which is positive. And we're concave up. Okay, concave up from 0 to infinity. Concave down from negative infinity to 0. Inflection point at 0, f of 0. So put that x value back into your function. So when you switch from concave down to concave up, you have an inflection point at that spot. Zero, 1. Part C, sketch the graph. Okay, so I'm pretty familiar with that function x cubed, and we're just going to shift it up 1, that parent function y equals x cubed. But using all of the work that we've done on the x-axis, put x equals 0. On this side, concave down. To the right, concave up. And what else? We're increasing the whole time, and we want to plot that inflection point, 0, 1. So we need to go through that point and increase the whole time like this. Increasing, concave down, still increasing and concave up. And that's our function. Okay, into the next chapter or next section, 4.4. L'Hopital's rule. Okay, so we did get through a little bit of this section, which means I'm going to do the short version of the rule and maybe one example, then we want to continue forward. So if f and g are differentiable, functions, and g prime of x does not equal 0 near x equal to a. Except possibly right at x equals a. Cool. And you have two situations that occur. Either the first one happens where limit as x goes to a, f of x divided by g of x is 0 over 0. Or, number two, limit x goes to a of f of x over g of x is infinity over infinity. Okay. Then you can use the rule. You can take the limit as x goes to a of f of x over g of x. And take the derivative of the top, take the derivative of the bottom, and it will be, this is all equal to the limit as x goes to a of f prime over g prime. Okay, so again, this is when you have 0 over 0 or infinity over infinity. Find the limit as x goes to 1 of x to the 7th over x to the 4th. Oh, x to the 7th minus 1 divided by x to the 4th. So just putting in 1, you'd have 1 minus 1, which is 0, divided by 1 minus 1, which is another 0. Okay, so take this limit. Apply L'Hopital's rule. Put a little h to say that we've done the rule. We still have that limit as x goes to 1 of 7x to the 6th minus 0 over 4x cubed. We will bring out 7/4 and then think about the limit after that. X to the 6 minus 3. So we have 7/4 times the limit as x goes to 1 of x cubed. And 7/4 times 1 is 7/4. So that's where we got to yesterday, just doing some different examples, and think we can keep going to different kinds of indeterminate forms. So there's indeterminate products, an indeterminate difference, and an indeterminate power. Products first. Okay, so if the limit as x goes to a of f of x is 0, and the limit as x goes to a of g of x is infinity, then the limit as x goes to a of f of x times g of x be 0 times infinity, which is an indeterminate form. Okay. Okay, of type 0 times infinity. So the strategy is to create a quotient by dividing the one function by the reciprocal of the other function. Or let's see, by dividing by the reciprocal of one of the functions. Okay. Create a quotient. By dividing by the reciprocal of either f of x or g of x. Okay, once you do that, you will have either 0 over 0 or infinity over infinity for your limit. which means you can use L'Hopital's rule and find the limit. I think we're just going to practice with an example, and that'll be enough. So I'm just kind of thinking like, I think it can fit here. So we're going to write f of x times g of x. So we could do, let's take the first function and write g of x dividing by the reciprocal of one of the other functions. So divide by 1 over f of x. So if you're on this side and go back the other way, you've got g of x, and then you would times by the reciprocal of the bottom fraction. So g of x times f of x over 1 gets you back here. Okay, now we'll try a problem. Limit as x goes to infinity of x times tangent of 1 over x. If you just put infinity in there, you'd have this going to infinity times tangent of 1 over infinity, which would be tangent of 0. Tangent is sine over cosine, which you'd have as 0 over 1. So infinity times 0. So we're going to rewrite this part as the tangent of 1 over x divided by 1 over x. So here, just kind of like that, we're going to have like scratch work, take this problem, carry it over here, and rewrite it. Okay. So we'll check this out. If we put infinity in, we have tangent of this becoming 0. So tangent of 0 is 0. And again, 1 over infinity, which means this becomes 0 in the denominator. And I can use L'Hopital's rule. Okay, again, that would be scratch work. Take this problem, carry it down, apply the rule. Limit as x goes to infinity. Derivative of tangent is secant squared of 1 over x. Multiply by the derivative of the inside. So you've got x to a negative 1 power, bring negative 1 down, and then subtract 1 from the power. And what are we doing? The derivative of the bottom function for L'Hopital's rule. Derivative of 1 over x is the same process. This is x to a negative 1 power. Negative 1 comes down. And multiply it with x to a negative 2. And then that term matches up with the 1 in the denominator. So what's left is secant squared of 1 over x. Okay, let's just put, let's take a limit. So x is going to infinity, which makes this go to 0, and we have secant squared of 0. Secant is 1 over cosine, so 1 over the cos, I'm just more familiar with cosine. Cosine squared of 0 would be 1 squared. So 1 over 1 is going to be 1. Sweet. And that's the end of that. Okay, the next one is an indeterminate difference. Okay, so we're looking at the limit as x goes to a of f of x equal to infinity. And the limit as x goes to a of g of x is equal to infinity. And then you look at the limit as x goes to a of f of x minus g of x. Being equal to infinity minus infinity, which is another indeterminate form. Okay, of type infinity minus infinity. Example would be something like this. We've got the limit as x goes to 0 from the right. Of 1 over x minus the sine of 1 over the sine of x. So first, just put that 0 in. We're going to 0 from the right side. So this is 1 over a very, very small positive number, which makes this equal to 0. So, wait. 1 over a very small, okay, so 1 over 0 would be infinity. 1 over something that's basically 0 is infinity. And then subtract 1 over the sine of 0, which is also 0. So we're subtracting infinity. Oh, I forgot to talk about strategy. So the strategy would be to algebraically manipulate the expression into a quotient of let's see. Unfortunately, that's not a really good strategy. It basically says use algebra. DRICKS, tricks. Okay, some of them would be like combining fractions, trying to factor. You could try to simplify. So let's combine fractions, which is what we're going to do. Maybe you can factor. Possibly simplify, etc. Okay, we're going to combine these fractions. So we'll have a common denominator of x sine of x. And take this limit. As x goes to 0 on the right. Sine of x over x sine of x. Minus x over x sine of x. So put those two terms together. The limit as x goes to 0 from the right. Let's see, the sine of x minus x over x times sine of x. Let's check this out. So we're putting in positive 0, or like we're approaching 0 from the right. So this is like the sine of 0, which would be 0, minus 0 is 0. Okay, 0 times 0 would be 0. So now I can do L'Hopital's rule. So that's some scratch work on the side. Come back over here and use L'Hopital's rule. We need the derivative of the top, and then we need the derivative of the bottom, which when we do that is going to have a product rule. Don't forget your limit. Okay, derivative of sine is cosine. Subtract the derivative of x, which is 1. Let's make this bigger. So we divide by derivative of the first time times the second function. Derivative of the first function multiplied with the second function. Add the derivative of this function multiplied by that function. Okay, derivative of this is 1 multiplied by sine of x. Add the derivative of sine of x is cosine of x times x. Trick is good. Okay, let's check this one out. So we put in 0, and we've got cosine of 0 is 1. 1 minus 1 equals 0. Sine of 0 is 0, plus 0 times 1, which is 0. 0 plus 0 is 0. So we need to do L'Hopital's rule one more time. We have the limit as x goes to 0 on the right. And then we get the derivative of the function in the numerator, then find the derivative of the function in the denominator. So derivative of cosine is negative sine. And we're going to subtract 0. Divide by the derivative of sine, which is cosine. And we do the product rule again. So the product of x and cosine of x will have a derivative of cosine of x times 1. Oops. Add. Derivative of cosine is negative sine of x, and then multiply that with x. So we're going to subtract x sine of x. Now I think we can go ahead and put that 0 in and get a number. So we've got the limit as x goes to 0 from the right will be negative sine of 0, which is negative 0. And now 0 in here. Cosine of 0 is 1 plus 1. So we've got 2 minus 0 times 0, which is 0. Okay. Negative 0 divided by 2 is 0. Let's see. That will be the end of notes for today. We have different types to talk about next time. There are 3 more types I'd like to cover. It's 0 to power. We'll write them really fast and then we'll come back and do notes on Monday. So we want to talk about something like 0 to the 0, infinity to power 0, and 1 to power infinity. So we'll cover those thoughts next time. Cool. Alrighty.